All right, good afternoon, everyone. We have an objective today, which is to almost finish the homework, okay? So hopefully we'll do that. If you have your computers, then I think you will not have much problem to do that. Before we get started, I wanted to ask you a question. When would you like to have the office hours for Javier? Javier told me he can make it Monday, 4 p.m. to 6 p.m. or Wednesday, 4 p.m. to 6 p.m. Any preference? Are you guys busy during that time? Do you have a class or something? No? Monday? All right. So let's do it Monday then. Let me change it quickly here. Okay. Good. So I think we have all the knowledge now in order to finish homework number 2. And let's start with that. So the first problem, it's a problem that asks you to calculate what is bulk mass density. And in this problem, it's slightly more complex than the ones that we saw in class, because now you have a rock which is made of 2 minerals, and that's going to change the equation a little bit. So let me here minimize this. Do you have any suggestion about how we could approach this problem? What would you do in order to solve it? Let me see if I can get this to work. So it's problem number 1. Give me a minute that I get set up here. Okay, so is that more or less visible? More or less, right? Let me try to zoom in to see I can get that a little bit better. Probably I'll use this one. Okay. In this problem, as I was telling you, you have to calculate what is the bulk density. And in order to do that, now that you have 2 minerals, you're going to have to utilize the volume fraction of each. So I'm going to write the equation, okay? If you have several minerals, then you will have to multiply 1 minus porosity. We used to do this times the density of the mineral, but now since we have 2 minerals, I'm going to do it for the general case. You will have to do the volume fraction of, let's say, mineral 1 times the density of mineral 1 plus the volume fraction of mineral 2 times the density of mineral 2. And if you had more than 2 minerals, it will be the volume fraction of that mineral times that density, and I'm going to explain a bit what that VI is. Well, actually I think I can do it here. So where B1 plus B2 plus all these volume fractions are equal to 1, right? So for example, in the case of 30% calcite, we should multiply 0.3 times the density of calcite. And for dolomite, 0.7 times the density of dolomite. Notice that 0.3 plus 0.7, that's going to make 1. So what I wrote just here, it's fine. And then you have to add to this the density of the fluid, right? Porosity times. And now let's assume the general case. In this case, this 100% filled with brine, but it may also fill with oil or with gas. So let's put an example in which we have oil and gas. If you have oil and gas and water, now you will have to multiply the saturation of water times the density of water plus the saturation of gas times the density of gas plus the saturation of oil times the density of oil. Again, the saturations, when you add them up, they have to be equal to 1. And this will be the general equation. So if you want to solve it now to this problem, I'll give you 4 minutes, and let me know if you have any question, and then we'll continue with the second one. Okay? I'll leave the equation here. As you work on that, let me tell you about the submission. I want you to submit everything online, but that doesn't mean that you have to work all the equations to type them on Word or something like that. You can work on paper and then just scan that and convert it into a PDF and then just submit that. You can also merge documents done on paper and done on your computer. I don't know if you guys are familiar with, there are several applications online that allow you to scan or to join PDFs and things like that. If you have Adobe Acrobat, you can do that, but you need a license, right? But you can go online. For example, let me see, which is the one I use? No, this is not the one I use, but you can use this one. You just drop your PDFs there, and then it will combine into one. I cannot find my. Okay, looks like one I was using is not popular anymore, but you can do that, okay? But again, I don't want you to type that on Word. That's not necessary. But then just take a picture and scan that. And for your phone, I think for scanning, I use an application which is pretty good, which is called, let me find, I think it's Cam Scanner. Yeah, Cam Scanner. And it's free. It has like a watermark logo, but don't worry, you can submit that. That's not a problem. Yeah. You can type it too. Yeah, but that's generally it's going to take you a little bit more time, but you can do that. In this problem, as I'm telling you over there, you have to look up for the values in the internet, okay, for calcite and dolomite. There is a good website called Crane's Petrophysical Handbook that usually has a lot of information there that it's useful for petrophysics and also for geomechanics. What? So which one is heavier, dolomite or calcite? Dolomite, right? Dolomite is heavier than calcite. Usually carbonate rocks with dolomite tend to be the heaviest rocks that you will find in nature, other than with some ferrous minerals. So for now, I guess just to save time, you can calculate the gradient later at home, but just calculate the density for now. What did you get as density? 2,626? Okay. Everyone got the same? All right. So remember, if you want to convert this to a gradient, you multiply times g in SI units. Otherwise, you just use that density and you use a proportionality that 1,000 kilograms is going to give you 0.433 psi per foot. Using that proportionality, you're going to get the gradient right away in psi per foot. And that's what we're going to do in a bit with the next problem. Okay, so let's go to the second one. Okay, in problem number 2, I want you to calculate vertical stress, but without the help of the computer. And the purpose of this problem is just to reinforce the general idea about vertical stress, and that is a result of an integral, and that you can calculate that integral if it's not too complicated, just on paper. And let's see this specific example. So it tells you that you are in an offshore location and you're interested in looking at vertical stress at 10,000 feet of depth. And I'm mixing a little bit units here because I also want you to get to know how to work in SI units. If you guys go to work somewhere in Europe or in Asia, very likely you're going to work in SI units. If you stay here in the US, you will work in English field units, but sometimes you may work on other projects outside, so you don't want to do a mistake with the units, because that's going to be very bad. All right, so let's continue then with this problem. All right, so here it says that you have a water depth of 1,000 meters, and then let me continue reading. You have to calculate this up to 10,000 feet, which 10,000 feet is about 3,300 meters, right? So let's assume this is our seafloor. And here I have 1,000 meters of water, and I'm interested in a location which is at about 3,300 meters, and I want to calculate what is the vertical stress at that point. And what the problem tells me is that I have a density of water remember that for vertical stress we use the weight of everything on top. So the density at the beginning is from 0 to 1000 is 1030. At the depth of 1000, the problem tells me that the bulk density starts to increase, and it goes at the seabed from 1800, so right at the point of the seabed I go to 1800, and for the next 500 meters it increases linearly to 2350. And then it stays relatively constant after that until the point I'm interested in. Okay, so now we have a density that varies with depth, and in order to calculate the total vertical stress we need to calculate the weight of everything on top, and the weight of everything on top is going to be given by this equation, and that's an integral of density times g. But I hope that you notice that geometrically, what is an integral? Where z is your independent variable and density is the variable that you're interested in and you're integrating as a function of depth. Let me add one more thing over there. This one is a function of z. So geometrically, what is going to be that integral? The area under the curve, right? So all that you have to do here is calculate this area. Multiply that times g, and you're going to get the vertical stress. So, for example, the first interval is going to be 1030, which is the height of the rectangle, times g times 1000. The second section is going to be the average of these two numbers, 1800 and 2350, which is the average height of this trapezoid, times 500 meters times g. And the last rectangle is going to be whatever this length is, that's going to be the base of the rectangle times the height, which is 2350 times g. And if you multiply all those numbers without doing any conversions, you're going to get your answer in pascals, right? If you divide that by 1 million, you'll get them in megapascals. If you divide that, if you multiply that times 145, you'll get them in psi. So I'll let you work in this on this for a few minutes, and then we'll continue, okay? So just as a reminder, I'm going to write the unit here. And what you're going to do it, what you're doing right now by hand is what we're going to do with the computer, and what we did also last class. It's just trapezoidal rule. But I just want you to see very clearly here where the trapezoid is. Let me know if you have any question, okay? Yeah.
So we should convert this from pascals to what?
To megapascals,
Okay.
and then
Move it over
to PSI.
to PSI.
Yeah. And just check that your numbers make sense, okay? Because here you are at 10,000 feet of depth, so you should get a vertical stress, total vertical stress SV, which is less than 10,000 psi. You should get something like 8 to 9,000 psi. So make sure that the number makes sense. Okay, small correction here. 10,000 psi is 3,050 meters. 10,000 feet, I'm sorry, is 3,050 meters. Yeah.
So is this how you would do it? You just add up like the areas and then just get like, I got it in kilograms per meter.
Okay, no, but don't forget to multiply times G, because you're
times
doing
G.
SI units.
Oh,
Yeah.
that's right. Okay. Thank you.
Where G is 9.8 meters per second square. I'm thinking on doing something like this for this class.
Yeah.
So I think it'll be very useful.
Definitely is. They got
Yeah.
most of this is just red stuff from Bauhaus.
Yeah. I know. I'm familiar
But all
with.
this stuff is like super useful.
Okay. So probably I'll do 1, 2 for my class. Yes. Sure. Did anyone get the answer? 7,000 what? So it's more or less 7,000 psi. closer to it. So okay, yeah, that makes sense. Makes sense to me. Okay, well, you should get something like around the 8,000 psi, okay? And if you divide that by 45, then you get the answer in megapascals. And I'm sure you can do this problem, but I really want to work on the next one. Actually, in problem number 4, then we'll come back to problem number 3. Because that one is the one that causes most of the problems all the time. All right, so we already worked a little bit in problem number 3. Problem number 3, if you remember, was the one for which we calculated vertical stress, and you copy that table and then you use it to calculate vertical stress. Okay, we're going to do something very similar, but now you're going to work with problem number 4. For problem number 4, we're going to use a real wellbore. And I have 2 files for that real wellbore. If you click on this link, let me just click open in another tab. Then you will get to this website where I have several files that are going to be useful to you for the entire course. And here also I have some of my Python scripts that I use in class. Feel free to take a look at them, to download them, to use them in your homework as you find them useful. And here, these are the 2 files that you're going to need. The LAS file and the .dev file. The first one, LAS, that's a typical and conventional format for a well logging file. And the second is a deviation survey. Alright, there are 2 options here. You can work directly with that LAS file, but it's a little bit more complex. Because of that, I already processed that file and converted it into a file that just outputs measured depth, sonic velocities, and density. And you're going to find that one if you go here to undergrad homework, go to homework number 2, which is the one that we're working on right now, and then you will find again these 2 files, the LAS file and the deviation file, and another file that has measured depth, travel times, and density. Before we open that one, let me show what this LAS file looks like. If you click here, you will go to this new page where it tells you that you cannot open this file, but you can go ahead and click view raw file, and this is what you're going to get. If you want to save this file, you go to your browser and look for save page as, and you'll see that it will save it as an LAS file. So you can do that. And I just want to, I don't know if you guys have taken information evaluation already. You have worked with LAS files, but this is a typical format that you use in order to have petrophysical data out of a wellbore. And here you see several things. For example, you see where the well log starts, where it finishes. You see other data like what is the wellbore, when this was done, and most importantly, you see what was measured over here. So for example, So let me zoom in because you may not see very well. But what here is telling you is that, let me zoom out a little bit now. The first column of data is depth in feet. Second one is bit size. Here you have description too, in inches. Caliper measurements, gamma ray over here, and we're interested in density. So here we have densities in gram per centimeter cube, and also we have a correction for density. And this is the data that we're going to use in order to calculate total vertical stress. You remember I told you that we will use the density log in order to calculate vertical stress of the real wellbore. Well, this is the case. And here's the data for all those measurements over here. Here now you have the data, and you're going to see that here's the depth, for example, and there are some weird measurements here like negative 999.25. That actually means no reading. It means nothing. So when you see that, it's just that there is no reading at all. The only true reading is this one over here, but all the others are not, they don't mean anything. Probably the tool wasn't deployed for those measurements at that time. If you continue going into deeper locations, you see that now all the readings are active, and those actually mean something. All right, so as I was telling you, if you're interested in working on this, feel free to work directly with the Elias file. It's going to be a little bit harder and more time, but you can do that, and this will be good training for the future. If you do not want to do that, the second option is to, instead to open that file, you can go ahead and open this other file, which I made, and it's a summary of now depth, travel times, compression and shear, and bulk density. I almost forget. Do you guys want to know where this wellbore is? Okay, I have it here. How would you do that? If you have all this information, anyone has a suggestion how we could get to know where this is? Here, you know, sometimes this data, I don't remember if I did or I received it already like this, but we don't see the company name, we don't see the location, but we have one piece of information that is going to let us know where this wellbore is. You were raising your hand? No? Okay, this is a wellbore number, and these first 10 digits are going to tell me where the wellbore is. So I went ahead and looked for this in drilling info, and this is where our wellbore is, the one that you're going to work with, a little bit offshore Louisiana. For those of you that are interested also in working in data, data processing, data mining, I want to let you know that we have access to drilling info, and I'm the manager for that. So if you want access to that because you want to work a little bit with it, you want to do, I don't know, a research project with it, just let me know. I can work that access for you so you can see similar data to the one I see right now. So let me zoom in again. This is the wellbore we're interested in. Here you have the number, and here you see a little bit more of data about the operator, its active, and where it latitude, longitude, and even if you have some production tests, and in this case, for some wells, for example, you have here the well logs, but in this case, it's not available here, but we have it, and I'm giving this well log to you. Okay? All right. So I don't know, just coming up with an idea of a research project, you could mine the data for these for all these well bores and tell me what is the vertical stress at the top of the Eagle Ford or any formation here in Texas or in any other part that you may be interested in. All right, let's go to the homework. Where was I? All right, I was here. All right, this is the file that you have to download, okay? So go ahead and get over here into this tab, and the next thing that you're going to have to do is you can go here. If you press raw, then you can save this file as a DAT file, and it's separated by tabs, but I'm not going to do that. I'm going to go another way. Actually, Excel changed the way to import data. I don't know how to use the new one very well, but what I'm going to do here is I'm going to select all of this. I'm going to copy it, and I'm going to paste it here. And this is what you should get as well. All right, so let me know when you're there. I'll give you 1 minute to get there because there is something else that you have to do now that I don't know if you know how to do, so I'll walk you to that step by step. And if you don't have your computer, then I'm going to upload this hopefully today, so you can also follow later from home. By the way, I updated the link to the YouTube channel for this semester, so you'll find it right there. Okay. Are you ready? Yeah? All right. Next step. You see that the data, it's we copied all of these, but it's not separated. We cannot work with that now because in every cell we have 4 numerical values. So what we're going to do is we're going to split that. And you're going to go to data, and from data you're going to go from text to columns. And in text to columns, you're going to click here on the first one, which is delimited. All right, then you press next, and on the delimiters, well, actually this data was separated by space, not by a tab, so you're gonna check the space box, and now you can see how your data is going to be separated and it's going to appear in different columns. You apply, you say next, and that's pretty much it. Finish, and now you have your data separated in columns. And let me fix this header because it should be density there. All right. Yeah. So I went into data, and in data I went to text to columns, and in text to columns I clicked on a box which says, instead of fixed width, says delimited, and in delimited you have to press next, and now you also check the box which says space. And next and finish. Okay, oh no, the problem is that you are not selecting all the data. You were just selecting one cell. You need to select everything, and so you either do what you're doing right now, or you do Shift Control down, and it will select everything at once. So in order to apply this to the entire data set, you need to select the entire data set, okay? So just, you know, to do it, to show that again, when I pasted this, it looked like that. And it was already selecting all the data. So don't click anywhere else. You need to select all the data in order to apply that to the entire data set. Okay. Are you there? Next step. Let's get rid of this 0.999.25. So what you're going to do is you're going to do a search and replace, which, if I remember correctly, you just press Control F if you have Windows, or if you have Linux. If you have Mac, you have to do Command F, and here instead of find, you click in replace. In Mac it's a little bit different. You need to open a tiny thing in the find window, and the replace is going to pop up. So we're going to look for this 99.25, and we're going to replace it with nothing. So we'll just leave it like that. And then we'll click replace all. Okay, actually replace it with some, let me see if I can, I'll put a space here.
Do you want the negative in there?
No, I don't want the negative, that dash. What? Oh, you're right. So let's see if now I can replace that. And I'm just gonna put a space. All right. I got rid of all of those. All right. So that's what I have right now. And as I was telling you, you know, if I put myself now in this cell over here, if I press Control and I press the arrow down, I'm going to find the first data point, which has some data. Wait. Not quite sure why this is not working, but this is my first data point. And it tells me that at the depth of 1887, I have density of 1.82. Let me do one more thing here, just to make this easier to work with. I'm going to freeze the panes, so I see this thing all the time. And this is going to be as a function of measure depth. All right, so you guys have that? All right, now we have to do something for which we have to use the next file. You remember that I told you that measure depth is not what we have to use. We have to use true vertical depth. And the reason for that is that measure depth, it just measures the length along the wellbore, and that's not necessarily the true vertical depth. So we need to obtain now the true vertical depth, because that's the one that's going to give us the total vertical stress. And actually we need the depth, in this case, below the seafloor. All right. In order to get that, we're going to use a deviation survey file. Okay? So, go back over here, and now open the deviation survey file. Just click there in that file, and you will see the data. I'm going to go again. I'm going to press draw. I'm going to copy everything, and I'm going to bring this to Excel. And I have my data over there. I'm going to do the same thing I did before. I'm going to separate it so I can work with that file. Delimit it, and this one was separated, already has tab and space, so that looks good to me. Just let me double check. Okay, there's just one minor thing that you have to fix over here, and you have to move this to here. So actually the name of the wellbore, it's all of this. So all of this is actually the name of the wellbore. So I could merge it or do something like that, but I'm not going to use it, so I just want to emphasize that this is the name of the wellbore is all of that. Okay, so now we have here measure depth and true vertical depth, and we have a few other things. Like for example, we have the east to west offset, or also called easting, north to south offset, or northing, and also here we have true vertical depth subsea, and also we have the location in a horizontal location X and Y of the wellbore. So what we want to get from here is TBD subsea as a function of the measure depth. So what I'm going to do is I'm going to do now something simple, relatively simple. If we had a wellbore that would be a little bit more deviated, we'll have to do something else. But let me plot here what is the true vertical depth subsea as a function of the measure depth. So let me add some titles to make it easier to understand. In the x-axis I have measure depth, and here I have true vertical depth subsea. So, do you think this wellbore is highly deviated? Do you think that it's relatively vertical? Does it kick off at some point into a lateral? What do you see in this deviation survey? Let me increase the font so you can see a little bit better. Any comment? It looks pretty vertical, right? Probably, you know, here it's very difficult to see a difference, but let's go to the last row over here. For this measured depth, we have a true vertical depth which is 50 feet less, more or less. So it's pretty much vertical, okay? But anyways, just for the sake of completing this homework entirely, let's here just use a simplification. Since this one is more or less in a straight line, I'm going to add a linear fit to this, and I'm going to use this equation that is going to tell me what is the true vertical depth as a function of the measured depth. Be careful that this is going to give me negative values, okay? So I'm going to use this equation in the previous Excel sheet. So let me write that down so I can write everything later on in the next sheet. So this equation, of course, is going to vary with your wellbore, but for this one it's pretty much a straight line. And let me come back over here. So now I can, from the deviation survey, I can tell you what is going to be the true vertical depth sub C. Let me change this color just to point out that it came from a different source. And I know that this is going to be equal to this is the equation that we just got from the previous correlation times this one plus 37.64. And this is also taking care of the elevation of the rig, that is not starting exactly at the sea level. So it's doing a few more things, that fixing this for to get the true vertical depth sub C. All right. So now I have the true vertical depth sub C. Now we're ready in order to calculate the total vertical stress. I'll give you 1 minute to catch up with me, and then we'll continue, okay? But this is the next thing that we're going to do. Just gonna make sure that my equation is okay. I'm gonna go to the bottom of the data set. Yeah, it's makes sense. It's a pretty similar value. In this case, you know, these values are similar, but if you have a highly deviated wellbore, they won't be similar. If you have a horizontal wellbore, these are going to be quite different. Yeah?
For some reason my best fit equation is different than yours. I'm not sure what I did.
Probably I think the columns you selected are not the ones that you should be selecting. Yeah, you see? You should use TBD sub C. Yeah. Yeah.
What did you do to like turn up the thing that with you?
Freeze panes. So go go here. A3. Just select A3 cell, and that's going to freeze everything which is on top and on the left of that cell. So then you go to view, you click on freeze panes on the right there,
Top.
on the top one, and now you can scroll down and then that's going to stay there.
Is it okay? I don't know why I guess I could just select all of these for the negatives.
And just get the yeah, you could do that, but I think it's just easier to modify the equation to add the negative on front,
Yeah.
and that's it. But you can do that too. It's going to be the same thing. All right, guys, are you ready? Okay, guys, if you're already there, the next thing that you have to do is you have to go to the cell with the first data point of bulk density. Okay? Are you all there? All right. So in this case, we don't have data above 1,887 feet. So since we don't have data, we have to assume something. And of course, there's going to be some error, some uncertainty there, but it's not going to be very large. And also, we know that this, as I showed you before, it's offshore Louisiana, so it's in relatively shallow water. So we're just going to assume that everything on top has that density. And that's what is going to help me to get a good guess for what is the vertical stress at this depth. So what I'm going to do here is I'm just going to assume that the first point is going to be equal to the vertical stress we will have if all the rock above had a density of 1.823 grams per centimeter cube. All right. So this one, I multiply it times 0.433, and I divide it by 1 because I know that 1 gram per centimeter cube is going to give me 0.433 psi per foot. And now I already have this gradient in psi per foot. And now the next thing I do is I multiply that times the depth, and I get the first value of vertical stress, which is about 1500 psi. Yeah.
Were you wanting to measure that there? Or?
Thank you. No. What I want is TVD sub C. That's why we calculated that one. Yes. All right. I have the first value, and the next thing I have to do is just to apply this equation over here, and the next value is going to be the one on top plus the average of the densities in the previous interval I multiply that times 0.433 and divide it by 1 just to make it obvious that we're doing this conversion over here, and I multiply now times the difference in depth because we're adding the weight of that thin layer, and that's going to be this one minus that one. And you can see that here our data now is very fine. It's every half foot, and that's a new value. Let me check the equation one more time. Seems correct to me. I don't know if you guys know this trick. You double click on that right bottom corner and it will copy everything and will copy all your equations. So let me check the last value just to make sure it more or less makes sense. It does make sense. And what I'm going to do now is I'm going to plot this. Okay? So let me plot it. Okay, remember to reverse that axis. So now we have here vertical stress, let me see why I cannot add axis titles. Okay.
Are you plotting measure depth or?
I'll check. I'm not sure. I think I'm plotting measure depth. Okay, let's check. Yeah, I was plotting measure depth. Let's do it with true vertical depth. And now it's true vertical depth. Just for completeness, let me also plot here let's plot density to see how that varies. So this is mass density. Let me write it. Bulk density. And you see that rock is about 2 grams per centimeter cube, and that increases as depth increases, and that makes a lot of sense. Okay, so work on that and let me know if you couldn't get what I got. Yeah.
This is this word equation? So use this equation.
And then, but you change the signs, right? Because this is negative values. These are negative values.
Like how do I change? Just switch.
No. This is your equation, right? And what are you using in the previous? Can I see what are you using in the?
This one.
Okay, and yeah, that seems correct to me. Okay, let me see again your equation. So the first is negative, the second is positive, right? Come back to your. Okay, then you reverse the signs, which is correct. And then yeah, this is good. Yeah. Yeah.
How do you, which one do you do? You do TV and density or S vertical?
I did both, right? I have one for bulk density,
Uh-huh.
and I have another.
How do you get S vertical again?
What?
How did you get the S vertical?
Oh, you didn't compute the S vertical yet?
No. Well, I thought it, oh, I think it's in the wrong.
Let me show you the equation. So the first data point is just, you can see the equation here on the top. Well, I can click so you can see a little bit better. It's just density times depth. And I assume that everything on top has that density. So that's why I just use one value of density. And I use the entire depth, because I consider that everything on top has that density. And for the next one, now I use an average of the density for that interval, and for depth I use the difference in depth, which is the height of that interval. Oh, there is a mistake there. Anyone sees a mistake? Yeah, actually it's true vertical depth. Sorry about that. So let me check. Yeah, this one is correct. This one is correct. So now let me. All right. Okay, now it's good. Now it's good. All right, guys, you have the answer. If you didn't get the answer yet, you have more time to work on that until Tuesday. There is just one more thing in the homework that you have to solve. And this is a problem. Oh, it's already on time. Just give me one more minute, guys. The problem is to calculate overpressure in with shale density. And in order to do that, you're going to have to follow this workflow, which is in problem number 2.6. So in 2.6, you see an example about how with shale porosity you can calculate effective vertical stress, and how with effective vertical stress you can get pore pressure. So in this case, I tell you in advance, pore pressure is not hydrostatic. It changes, it increases at a certain point. Okay? Just let me know if you need any help. Javier and the tutors also will be available to help you. All right? Have a great weekend.